this situation where we have two mountain climbers partway up a mountain, and they clap their hands to hear the echoes return from the mountain face opposite them in 6 seconds. And so here we have like our mountain, if you like. Here's our mountain climber. They send a clap. He comes back again. Takes 6 seconds later. Like clap, and then 1,000, 2,000, all the way up to 6,000, right? So we say, okay, well, the amount of time it takes is 6.0 seconds. The temperature, according to this problem, is -5 degrees Celsius. The speed of the clapping sound is, I don't know what. And the distance away that they are from the mountain is, I don't know what. Well, first of all, the answer to the I don't know what about the speed of sound is going to be time dependent. So 332 meters per second plus 0.590 times 10 to the power, not 10 to the power of, oh goodness, here I am stuck on scientific notation. 5.90 meters per second degrees Celsius times the temperature in degrees Celsius. Remember, there's two different variants to this equation depending on whether you're doing a textbook problem or workbook problems. One of the equations is, I think, done at sea level, and one of the equations was not determined at sea level. That, I think, is what the discrepancy is, but it's an experimentally determined equation. Remember, the experimentally determined equation is based on the speed of sound as a function of degrees, temperature in degrees Celsius, and it came from an experimental graph that looked like this, where y equals mx plus b. The b-intercept is 332 meters per second, and the slope is 0.590. And so, yeah, it's not like a derived equation. It's an experimentally determined equation. So if you see different versions, that's the reason. But when we sub in our values, the temperature is -5 degrees Celsius, and we end up getting 329.05. I almost made a mistake there, meters per second. Cool. All right. Well, then people say, well, how does that help us figure out how far away the mountain is? Well, there's this little equation from kinematics, delta d over delta t is equal to speed. And if I want to isolate for delta d, I could sub in my values, unrounded, of course. And it took 6 seconds to travel to the mountain and back. So that means that sound had to travel 1,974.3 meters. Of course, when I look at my diagram, the sound had to travel to the mountain and back again. So this distance is actually traversing the gap twice, yeah? So that doesn't tell us how far away the mountain is. That tells us, that tells us twice the distance to the mountain. You see what I mean? So we're going to take that value divided by 2. Delta D equals 1,974.3 meters divided by 2. Really? 987.15 meters. So we got to be thinkers about this. And since the time only has 2 significant figures, I guess we're at 9.9 times 10 to the power of 2 meters away, 990 meters away. Now, some people, sorry, I'll just answer a question in a minute, but some people I overheard said, oh, instead of dividing by 2 the way that I did it, some of you divided time by 2 to make it be 3 seconds, right? Because it's going to take 3 seconds to go a one-way trip. That is also an equivalent way of dealing with this. How many people divided time by 2? Yeah, half the room, right? So it's a 50-50 shot on this one. Is that what you were going to ask me? Yeah. Okay, sorry, I read your mind. All right, the next question is, and it's an ABC question. It says that there's a tone generator. So let's say it's like a speaker, okay? A tone generator which vibrates at 300 hertz is placed in a swimming pool full of water. All right, so the frequency of the speaker is 300 hertz. Now in water, the speed of sound in water, it says, is 1,498 meters per second. The speed of sound in air is 331 meters per second. Now somebody pointed out that if it's 331 meters per second, then the air must be just below 0. And then they reasoned that the water, therefore, must be just below 0. And so we're talking about this being a block of ice. You guys know that just because it dips below 0 doesn't mean that the entire lake freezes solid instantly, right? Are we okay with that? All right. Also, it could be salt water. which case it's going to freeze at a lower temperature anyway. So let's suspend our disbelief on that one, okay? And I appreciate the challenge of logic, but we're going to kind of roll with this as it is, if we're okay with that. I know that my swimming pool, although I always close it before it gets to sub-zero temperatures, I know it wouldn't freeze solidly instantaneously. Neither does the lake nearby. All right, so we've got a speed of water and a speed in air. And the question is, state the frequency and wavelength of the tones transmitted through the water. Okay, so we're thinking about water now. Now the speed is going to be, as we said, 1,498 meters per second, but we also know that speed is equal to lambda times f. If I want to figure out the wavelength, lambda is equal to v over f. Seems to me that that means I need to know the frequency before I get started. Wait a minute. If this is a tone generator and I put it underwater, think about it. Here's a speaker. If I put it underwater, it's going to vibrate at 300 hertz. If I lift it out of the water, what frequency is it going to vibrate at? 300 hertz. It's the same speaker. So the frequency is still 300 hertz, whether it's above water or below water. Well, that answers that question. So when I go to calculate the lambda value, 1,498 hertz, or meters per second rather, divided by 300 hertz, I end up getting 4.993 meters. Of course, I'm going to round that off to the appropriate number of significant figures, but I kind of want to keep things moving because this is just supposed to be a quick take-up of some try this questions, okay? Part B says, state the f and lambda, the sound wave that's in the air. Well, by the same logic, couldn't we just say lambda is equal to v over f? And if it's 300 hertz below water, it's going to be 300 hertz above water because it's the same speaker that's playing. Did you guys know that when you listen to a sound below water, it's actually the same frequency as the sound above water? And there's always people that say, no. I've heard sounds. When I'm in a pool and there's a party going on up above the water, pool party, I hear the sounds that go, you guys ever try to hear a noise when you're underwater? It sounds like all muffled. It's not changing the frequency. What's actually happening is your ears are not designed to operate underwater. So your ears don't pick up the vibrations very well. So it feels not crisp. That transition of the vibrations from air to water, back to the little air pocket that's inside of your ears, causes a muffling effect. It didn't change the frequency. Okay, the frequency is still the same. I bet you if you scream at a dolphin, don't do that. They're gentle creatures. But if you scream at a dolphin, maybe they're not. I don't know. Depends on if you're a jellyfish, I guess. Anyway, if you scream at a dolphin, they're going to hear the same frequency as the people above water because their ears are what? Tuned to underwater or not tuned to underwater? These are aquatic mammals, right? They're going to be able to hear just fine. Anyway, the frequency underwater is still going to be 300 hertz. And speed, though, is 331 meters per second over 300 hertz. And so that means that the wavelength ends up being, I get about you guys did the math before me, 1.103. Does that sound right? Yep. All right, sweet. Now the question is, why would you hear the same frequency of sound above water as below water? Answer is, I'm just going to say it out loud. The answer is because this thing's vibrating at the same frequency. So if it vibrates into water particles, it'll vibrate into water particles at 300 hertz. If it vibrates into air particles, it'll vibrate into air particles at 300 hertz. That's all. It's just a speaker that's bouncing in and out 300 times per second. That's all. I want to take a look at this picture down below. I got these two students. These two students are wiggling ropes. Yes. C doesn't make sense? Oh, no. Here? Oh, okay. Well, let's encounter C as we encounter it then. Okay. So I get these two students that are wiggling ropes. And I'm going to throw in a principal axis here just so that I can make sense of things in terms of standing waves, which is kind of one of the topics of the day. And I see that the student up at the top, I'm going to call the student at the top student 1 and the student at the bottom student 2. And as they wiggle their ropes, the question is, which skipping rope has more wavelengths that fit in? And everybody all at once says, let's hear it one more time. Student 1, yeah. So I'm going to put Student 1, more wavelengths fitting into that resonating rope. Notice the ropes are the same length. What harmonic is shown on each skipping rope? Can you count it out? Yes?
Isn't it 4 for the first one, 2 for the...
It's not 4 and 2. Yeah?
Is it 7 and 2?
It's 7. This one's the 7th. That's the 7th one. What's the next one? It's not 3. We've got to be careful. And I'm going to give the cartoonist a hard time here. Can you guys see that there's 1, 2, 3, 4? Okay? Not a perfect cartoonist. It wasn't me. It was somebody else. But still, this is the 4th harmonic. Okay? Part C, assuming the skipping ropes are both, and then it already got brought up, part C doesn't make sense. You're right. I got a typo here. I must have rushed my typing. Let's make this be a 10-meter long rope. What wavelengths are present? So for this 10-meter long rope, here's our L value. I want to put out, and we said this once before, that the length is equal to n times lambda over 2, where n is an integer number of half wavelengths. And if I want to figure out the wavelengths present for the first one, I could rearrange this equation, and I would get 2 times L over n is equal to lambda. What's the n value for the first one? 7, yeah. So for this first one, I would say, okay, well then the wavelength for the first one is equal to 2 times L over 7, or lambda equals 2 times 10 meters over 7. Who's already calculated it? What's the wavelength? Yeah, back over here.
2.857.
Nice. 2.857 meters. That's the wavelength for the first one. I could round it off to significant figures, but I kind of want to keep things moving a little bit. Yeah? No. The integers don't count for significant figures. And I think we covered that in a previous lesson, but I'll just say it louder for everybody. The n value does not impact significant figures. You either count a wavelength, it's either present or it's not, okay? So there's no sig figs associated with integer counts. The second one here, we could do the exact same process, same formula. We say, okay, lambda is equal to 2 times L over n, where this time it's 2 times 10.0 meters divided by n equals 4. Actually, 2 divided by 4, that's just a half. Half of 10 is 5. So lambda is equal to 5.00 meters. All cool, okay? Now that's the process for C. But for D, which of the two standing waves requires more energy? Now this, I think we need to work our imaginations up a little bit. If I was going to make this happen, am I wiggling fast or slow? This one here, I'm wiggling relatively slow. Would you believe that, which one takes more energy? Number 1 or 2? Everybody shout out the answer. 1. Everybody says 1. This is going to take more energy, right? Now, as it turns out, this is D we're talking about. The energy that it requires to keep a standing wave going is proportional to the frequency, right? You would have to have a higher frequency to do that first situation. In fact, we could even say that the energy is proportional to the N times F1. Wouldn't that be the same thing? Makes sense, right? More energy for higher frequencies. So it's going to be 1, but for that rationale. In fact, this shows up in quantum physics. This idea of standing waves and integer counts of harmonic numbers. This is a cornerstone of quantum physics. And I suspect, I'm not the curriculum designer, but I suspect that that's why this is in the curriculum at this stage, not only to learn how musical instruments work, but to throw in just like a little foundational understanding for how quantum works too. And we'll come back to it in grade 12 for sure. E, which is the higher frequency? Well, I feel like we kind of answered that. Which one is it? Number 1, yeah. Now, if you wanted to have some math to back that up, not just your general feelings, we'd say, hey, if the speed of a wave on the strings is the same for both waves, doesn't it make sense that V is equal to lambda F? So larger wavelengths will have lower frequencies because V is a constant, whereas lower wavelengths, smaller wavelengths, will have higher frequencies. Sounds good? I'm going to stop there on that one.